All right, and we're back. All right, so part 2. So I hope this is part 2, not part 3. It's always hard to tell with this camera. Centripetal versus centrifugal force. What are they? If you're in circular motion, there are two types of forces. There's a force that pushes you inwards and a force that pulls you outwards. Any forces that pull you inwards are called centripetal forces. Now, there is no specific centripetal force. Centripetal forces include but are not limited to gravity, friction. Those are the only two I can come off the top of my head. Or if you're spinning a ball around, usually you're pulling inwards as you spin the ball around, you are the centripetal force. Centrifugal force is a very specific force that has an actual equation for it. Now, it's sort of a pseudo force that it doesn't really exist, but what it does is it keeps you, it's a force that tries to oppose your circle. The reason being is that if I take this pin and I spin it around and I let it go, at any given point, what direction do you think it's going to fly? So if I spin around like this and let it go over here, what direction do you think it's going to go? Do you think it's going to go this way, or that way? So go ahead and think about that for a moment. Make your prediction. Have your cat make a prediction. I don't know what my fascination is with cats who watch YouTube. Have your next door neighbor, roommate, make a prediction. All right, so let's test it. They went that way. The reason being is it's traveling this way, and so when I let it go, there's no longer forces to keep it in circular motion. There's no longer centripetal force, and so it flies outwards. Now, from the perspective of the pin, it feels like it's being pushed outwards by what's called the centrifugal force. And the equation for the centrifugal force, which I wrote as F sub c, is the mass times velocity divided by your circular radius. And it always points outwards, directly away from the center of the circle. In fact, when you're in orbit around the Earth, the gravitational force will exactly cancel out the centrifugal force, meaning that you'll have no net force on you and you'll be weightless. So go ahead and do this one. The numbers are kind of big, but hopefully you can do the math. If you don't want to plug the powers of 10 on your calculator, 10 to the A times 10 to the B equals 10 to the A plus B, and 10 to the A divided by 10 to the B is 10 to the A minus B. So you can do those without plugging them on your calculator. Just plug the numbers in front. Go ahead and do parts A and B. We have a 3,000 kilogram spacecraft at a distance of 6.5 million meters, or 10 times 10 to the 6th, and a velocity of 8.2 times 10 to the 3rd meters per second. So calculate the centrifugal force, and then compare that to the gravitational force, and just go ahead and use mg here, because at that distance it's about, g is still about 9.8. In fact, I encourage you to actually use 9.8 here instead of 10. Because otherwise the difference will be a little bit greater. Go. I had to stop there before Price is Right sues me. All right, and we're back. So, centrifugal force equals mass times velocity over radius. This is a level 1 problem because I'm just sticking in numbers into this equation. So I've got the mass of 3,000. I'm actually going to write 3 times 10 to the 3rd. This can make math a little bit easier. Times 8.2 times 10 to the 3rd meters per second squared divided by 6.5 times 10 to the 6th meters. Now here's some fancy math for you. I'm going to have 3 times 8.2 times 8.2 divided by 6.5. Plug that in the calculator. Times 10 to the 3 plus 3 plus 3 minus 6. So 3 plus 3 plus 3. So I squared it, minus 6. So this is 10 to the 3rd. 8.2 squared is 64 plus 3.2 plus 0.04. Ignore that. So that's 67.2 times 3 divided by 6.5 gives me about 10 points here. We have 2.2, 10.3 times 3. So that's about 31. That's 3.1 times 10 to the 4th newtons. If I have done my math correctly. All right. Gravitational force. Actually, I'm just going to use 10 for G. mg, which is 10 times 3,000, which is 30,000 newtons. So you can see they're pretty close there. I think the velocity may be a slight bit too high. Slight bit too high. All right. But that's only when you're in orbit that they're equal. Angular momentum. Now, I'm not going to get too far in depth in angular momentum. If you're in a trig-based class, you're going to do a lot with angular momentum and angular momentum conservation. Number momentum is mass times velocity, and so the mass goes to inertia, the velocity goes to angular velocity, so angular momentum, which is denoted with an L, is inertia times angular velocity, or mass times velocity times radius. We're really not going to do much with that in this class, though. But we are going to do the concept. So, we have angular momentum, and just like linear momentum, it's conserved. And this actually has very important repercussions for our planet, namely our climate. So angular momentum is conserved. So if I'm rotating, my momentum stays constant, even if my radius does not. So we probably have seen the ice skaters at some point, and they pull in their arms, and as they pull in their arms, they speed up, and as they do this, they slow down. The same is true about planet Earth. If I draw planet Earth on the board, you can see that if you're standing here in Indiana, wow, you're tall, you have a much smaller rotational radius than if you're on the equator. And so if you were to go south, your radius would increase effectively. And if you go north, your radius effectively decreases. And this has an effect on wind patterns. And this creates what's called circulation cells. So we have 3 circulation cells on Earth. The equatorial one's called the Hadley cell. And then you have the polar cell, which we're becoming very, very familiar with in the winters. And then we have a center cell, which is a pseudocell. It's sort of like a cog in the middle of 2 bigger cogs that rotate the center cog. And that's why here in Indiana we get so much push and pull in weather, particularly in winter, because the equatorial cell and the polar cell are pushing on the center, and they push back and forth, and that creates dips and rises in the jet stream. And the position of the jet stream vastly affects our temperatures in any given part of winter. And if the jet stream gets pushed to the north of us, we have a very warm week. And then if the jet stream the next week gets pushed to the south of us, it gets brutally cold and lots of snow. And so, but this is all driven because of angular momentum. Now, the air on the equator gets the most energy from the sun, and so it rises. Now we're ignoring the seasons for just a moment because the effective equator shifts north and south over the course of the year, and so it shifts the polar cells over the course of the year, which is why we get different weather in the winter versus the summer. But when the equator is on the equator gets the most energy. That air heats up. As it heats up, it rises and spreads out, and then moves to the north and south, away from the equator. Since air is moving away from the equator becomes a permanent low pressure zone. Air goes from high pressure to low pressure. We'll learn more about that later in the course. And so along the ground, the air goes towards the equator. Now the air that's coming south from the middle latitudes is now going to a larger and larger radius, which means that as it gets to a bigger radius for angular momentum to be conserved, which is mvr, as the r gets bigger, v has to get smaller. Remember, it's rotating around the Earth once per day. So as v gets smaller, it has to rotate slower around the center of the Earth, which means it takes more than one day to go around the Earth. From the perspective of the ground, which is still going once per day, it appears that the air is actually going down to the west. That's why if you go to Hawaii, the winds go to the southwest instead of to the east like they do here in Indianapolis. They call those the trade winds. Because the air is going towards the equator, and as it goes towards the equator, it gets pushed to the west. And then there's this convergence zone at about 30 degrees, just a little shy of 30 degrees latitude. That's a permanent high pressure zone. A lot of the deserts on Earth are at this location, both in the northern and southern hemisphere. The Sahara Desert, the deserts of Mexico and southern United States are there, because that's a permanent high pressure zone. In India, for example, they only have the high pressure zone over India for half the year. The other half of the year is actually over the Indian Ocean. And so the high pressure zone pushes a lot of hot, moist air over India, and they get their monsoon season. However, as climate temperatures go up, the polar zone becomes more powerful, and it pushes the high pressure zone north. At some point, it is very possible that even in the winter, the high pressure zone will lie over India, and the monsoon season will go away almost completely, if not completely. That'll be a big problem for India in the next 100 to 200 years. And then, of course, in the middle region, we have the polar zone pushing down. Along the ground here, it usually goes to the north. As it goes to the north, the velocity has to increase, so it goes to the east. And so that's why our jet stream pushes to the east. And so the circulation patterns of the Earth are all based on conservation of momentum. In fact, rotations of hurricanes are also based on rotational angular momentum. So a hurricane in the northern hemisphere is a low pressure zone. So the air goes north towards it, and as it goes north towards it, it goes this way. The air coming from the south goes that way, and so it rotates clockwise. In the southern hemisphere, it does the opposite, it rotates counterclockwise. And that's all because of what's called the Coriolis effect, which is all due to conservation of angular momentum on the Earth. But what about toilets? There's always the rumor that toilets would spin backwards in the southern hemisphere because the rotation is different. So if I took my toilet at home and took it to Australia, what direction would my toilet rotate? And if you're guessing clockwise, you'd be incorrect. If you're guessing counterclockwise, you'd also be incorrect because my toilet at home doesn't rotate, it just goes straight down. Well, let me tell you sort of an anecdote. When I was in grad school, one of my astronomy professors, for those who are watching the first time, I'm actually an astrophysicist, but I teach lots of physics, although I focus on the bigger picture sometimes, such as here. Went to a village in Africa, and there was a person that had this basin, and filled it up with water, with leaves on the top so you could see what direction the water rotated. declared himself in the northern hemisphere, and it rotated one way, I forget which way, it was clockwise. Then he went to the other side of the village, declared himself in the southern hemisphere, filled up the basin, put the leaves in, and sure enough, they rotated the opposite direction. Then he went halfway into the village, in the middle of the village, declared himself on the equator, and did it again, and it went straight down. Sounds like my decree of toilets not being affected by hemispheres bash, doesn't it? There was only one small problem with the story. The particular village in Africa was nowhere near the equator. Nowhere. And so it was all based on design. In fact, the directions your sinks and toilets drain is all based on the design of the plumbing. You can design the plumbing to get it to rotate clockwise or counterclockwise or just go straight down. It's all based on plumbing. In a span of this much distance, the rotation of the Earth does not change enough for the Coriolis effect to have any actual amount of force that would be noticeable in any way, shape, or form. The surface tension of the water would be many orders of magnitude greater than the Coriolis effect over the toilet. So the Coriolis effect affects the climate of the Earth, affects our weather patterns, it affects hurricanes, but it does not affect our toilets. So to wrap up, we've learned everything we could possibly want to know about angular motions. We've learned that there's a good relationship between the linear world and the angular world. So if you understand the angular motion equations, the linear motions equations, the angular ones are not so bad. There's a translation between the two. Torque's a little bit tricky. Other than that, once you have the hang of the linear ones, you pretty much have the hang of the angular ones. And there's a translation where the linear world equals the angular world times r, except for torque. And that's all we have for this particular lecture. I will see you all in recitation for those in my class, and for those who are not in my class, I guess I'll see you in the comments section. Maybe.